Covered on July 1st by the NASA-funded Atlas survey. It was discovered.
Imagine a giant traveler from another star system, older than our sun, tearing through space at over 130,000 miles per hour. Scientists call it 3I Atlas, and it's rewriting everything we thought we knew about comets. Its dust falls toward the sun when physics says it should blow away. Its chemistry is silent when it should roar with activity. Its path weaves between planets with impossible precision. What is this thing, and why does it defy the rules of the universe? 3I Atlas was first spotted on July 1, 2025, by NASA's Asteroid Terrestrial Impact Last Alert System, also known as ATLAS. A telescope located in Rio Hurtado, Chile, picked up a faint moving point of light in the constellation Sagittarius. At first, astronomers believed they had found another routine near-Earth object.
Barely inside the orbit of Mars, and then it's going to keep going on its way out of the solar system. From images, we also saw that this object is active, which means that around the nucleus there is some coma, which is an indication that this object is in fact a comet.
These are common discoveries, and the system was designed to track them. But within a matter of hours, the calculations of its orbit showed something unusual. Its path was not the closed ellipse of a body bound to the sun, such as an asteroid or comet. Instead, its path was hyperbolic, an open curve that signaled a different origin. This was not something orbiting our sun. This was an object passing through from interstellar space. That is why the name was given, 3I Atlas. The 3I stands for the third interstellar object, after 1I Oumuamua in 2017 and 2I Borisov in 2019. Just like those earlier discoveries, Atlas captured global attention immediately. Astronomers all over the world knew how rare this opportunity was. But the 3I Atlas turned out to be very different from its predecessors. Oumuamua was small, only about 200 meters long, and never showed signs of comet-like activity. It looked more like a tumbling fragment of rock. Borisov, on the other hand, behaved much more like a traditional comet with a tail of gas and dust. But 3I Atlas is larger, more complex, and, most importantly, far stranger than either of them. Early size estimates suggested a nucleus as wide as 7 miles, making it the biggest interstellar object seen so far. Later measurements refined that number to about 3.5 miles, still very large compared to the first two. For context, Halley's Comet, one of the most famous comets in our solar system, is around 7 miles across. The chance of spotting an interstellar object this large is extremely small, less than 1 in a million, according to some statistical models. That makes the discovery of Atlas especially puzzling, since it was found by a survey designed for near-Earth asteroids, not by a deep space search. At first, Atlas appeared to have the features of an active comet. A hazy cloud of gas and dust, called a coma, surrounded it. This was expected. But when scientists took a closer look, the behavior of the dust raised questions. Normally, comets are made of ice, rock, and dust. As they approach the sun, the heat causes the ices to sublimate, meaning they turn directly from solid to gas. This releases dust into space and forms a bright coma and a tail. Because of the sun's radiation and solar wind, the tail always points away from the sun, no matter what direction the comet is moving. Atlas, however, seemed to ignore this rule. On July 21, 2025, when the Hubble Space Telescope took its sharpest images, it revealed a dust plume streaming toward the sun rather than away from it. To understand how strange this is, imagine a kite flying directly into the wind and holding its shape there. Solar radiation should have pushed the dust outward, yet Atlas's dust stubbornly clung to the sun-facing side. If the dust was not behaving normally, perhaps the chemistry would provide answers. Comets usually show very distinct chemical signatures. When gases are released, they glow at specific wavelengths, allowing scientists to detect substances such as cyanogen or diatomic carbon. These emissions are like fingerprints, easy to spot with the right instruments. But in the case of Atlas, the spectrum was nearly blank for weeks. Despite being visibly active, it did not show the usual chemical signs. Only much later, when it moved closer to the sun, did faint traces of cyanogen appear. This combination of a sunward dust plume and missing chemical fingerprints forced astronomers to search for explanations. One suggestion is that the surface of Atlas has been hardened by cosmic radiation over billions of years in interstellar space. A crust like that could delay the release of gases until the object was much closer to the Sun. Another idea is that the comet's rotation is tilted in an unusual way, causing only certain regions to heat up and release material. Yet neither of these theories fully explains the strange dust orientation or the late appearance of chemicals. New data soon added to the mystery. On August 6, 2025, the James Webb Space Telescope observed Atlas with its near-infrared spectrograph. It detected an enormous cloud of carbon dioxide stretching hundreds of thousands of kilometers. The comet was losing CO2 at a rate of about 70 kilograms per second, but the amount of water vapor was very low, less than 5 kilograms per second. This is highly unusual because most comets are rich in water ice. In fact, water is normally the dominant component. Atlas, by contrast, seemed to prefer carbon dioxide. The implication is that Atlas may have formed in a very cold region of its original star system, near the so-called carbon dioxide ice line. This is the distance from a star where temperatures are cold enough for CO2 to freeze. If that is the case, then Atlas could be a preserved fragment of a planetary disk very different from our own solar system. All of this was intriguing enough, but the trajectory of Atlas made it even more remarkable. Most interstellar objects we expect to pass quickly through and then leave. Atlas, however, was on a path that threaded through our solar system in a series of close encounters that seemed almost impossible. On October 3, 2025, it was set to pass within 29 million kilometers of Mars, close enough for orbiters around the red planet to take detailed images. A few weeks later, on October 30th, it would reach perihelion, its closest point to the Sun, at a distance just inside the orbit of Mars. Then on November 3rd, it would swing within 0.65 astronomical units of Venus, a region rarely crossed by comets. Later, it would also skim past Jupiter. Statistical simulations suggested that the odds of such a sequence of close approaches were extremely low, around 1 in 20,000. On top of that, Atlas's orbit was nearly aligned with the plane of the solar system, with an inclination of only 5 degrees. The chances of a random interstellar object entering at such an angle are about 1 in 500. This improbable trajectory sparked debates within the scientific community. A small group of researchers even proposed that Atlas's path might not be entirely natural, raising the possibility that it could be a technological object using planetary flybys in a controlled manner. The idea was highly controversial, and most experts regarded it as speculation. The majority agreed that Atlas is a comet, though one with features that push the limits of our understanding. Even so, the anomalies cannot be ignored. Its enormous size compared to other interstellar objects, its strange dust plume, its missing chemical signals, and its unusual path through the solar system make Atlas stand apart from anything else we have seen. For astronomers, each of these details represents not just a puzzle to solve, but also an opportunity to learn more about how planetary systems form, evolve, and sometimes eject material into interstellar space. When astronomers dug deeper into 3I Atlas, more anomalies emerged that made it stand out from both ordinary comets and earlier interstellar visitors. One of the first things noticed was its unusual pattern of brightness. Normally, a comet's brightness changes as it rotates or as bursts of gas and dust erupt from its surface. These variations tend to be irregular, or they follow the expected timescale of a rotating nucleus, which is usually measured in hours or days. In the case of Atlas, however, data showed a repeating signal. Advanced analysis techniques, including artificial intelligence tools designed to filter large data sets, detected a consistent rhythm in the comet's light curve. This repeating pulse looked less like random noise and more like a steady beat, a kind of cosmic metronome. The statistical confidence of this finding was extremely high, far above what would normally be dismissed as coincidence. This discovery puzzled scientists. A comet nucleus several miles wide should rotate with a certain period, but the light pattern observed in Atlas did not match what models predicted for a body of its size. Some speculated that the pulse might come from a reflective patch on its surface that happened to catch the sunlight at regular intervals. Others wondered if structural features or unusual outgassing events could be behind it. Yet the consistency of the signal across different telescopes, including Hubble, made these explanations less convincing. For many, this was another unexplained layer added to an already mysterious object. Another aspect that caught attention was the way Atlas moved through space. When its orbit was calculated, astronomers expected a purely gravitational path, influenced only by the sun and the planets. But detailed measurements revealed a small, persistent acceleration that could not be accounted for by gravity alone. The value was around 10 to -7 meters per second squared, too large to be dismissed as an error, but too small to be explained in the usual way. Ordinary comets often show non-gravitational accelerations because of outgassing. As ices turn into gas and jet into space, they act like tiny thrusters, pushing the nucleus slightly off course. But in Atlas, the acceleration appeared before strong signs of outgassing had even been detected. Moreover, the chemical signatures that would normally explain such behavior were absent or delayed. That left researchers with few options. Some suggested the nucleus might be unusually thin and reflective, allowing sunlight to push it like a natural solar sail. Others pointed to exotic ices such as nitrogen or carbon monoxide that might sublimate in unpredictable ways. Still, no single model explained the observations completely. These peculiarities inevitably led to speculation about whether Atlas could be artificial in origin. The idea had already been raised with Oumuamua in 2017, largely because of its odd shape and unexplained acceleration. With Atlas, some scientists published cautious papers suggesting that its precise flybys of Mars, Venus, and Jupiter, combined with its low inclination, might point to a trajectory that was not entirely random. They even proposed that it could, in theory, be using a maneuver similar to what spacecraft do when they use planetary gravity to adjust their paths. Most of the scientific community remains unconvinced. The evidence still strongly supports Atlas being a natural comet, albeit a very unusual one. The dust, the traces of carbon dioxide, and the delayed detection of cyanogen all point to a composition consistent with natural origins. While the anomalies remain unresolved, they are not yet proof of anything artificial. Scientists stress that extraordinary claims require extraordinary evidence, and so far the balance of data leans toward a natural explanation. Even with that caution, Atlas offers valuable lessons. Its composition suggests it formed in a very different environment from our own solar system. The dominance of carbon dioxide over water ice indicates it may have developed in a region far from its parent star, where temperatures were low enough for CO2 to freeze, but where water ice may have been scarce. Its estimated age, between 7 and 11 billion years, makes it far older than our Sun. That means it could be a remnant from the early days of the Milky Way, a frozen fragment of a planetary disk long vanished. Its journey to our solar system likely began with a violent event. Models suggest that interstellar objects are ejected when planets or stars exert strong gravitational forces, flinging them into interstellar space. Atlas could have been expelled from its home billions of years ago, wandering the galaxy ever since until chance brought it close to Earth. In this sense, it is like a time capsule, carrying with it the chemical and physical record of another star system's earliest days. As Atlas approached the inner solar system, astronomers mobilized every instrument available. The Transiting Exoplanet Survey Satellite, better known as TESS, had already recorded signs of activity as early as May 7, 2025, when the comet was still 6.4 astronomical units from the Sun. That distance is further than Jupiter, suggesting Atlas had been active longer than most expected. Observations from the Neil Gehrels Swift Observatory in Gemini South added further detail, including evidence of water ice and hydroxide ions, which pointed to a complex icy structure beneath its surface. The European Space Agency is preparing a mission called Comet Interceptor, planned for launch in 2029, with the specific aim of visiting comets and interstellar objects. Unfortunately, it will not be ready in time for Atlas. By then, the comet will already be gone. Proposals were made to redirect spacecraft already in space, such as NASA's Juno mission or orbiters around Mars, in the hope of capturing close-up images. But practical issues like fuel and trajectory made such missions unlikely. For now, ground-based and space telescopes remain the main tools to study it. As Atlas continues its path, astronomers expect its coma to grow larger and its chemistry to change as new layers of ice are exposed to solar heat. By the time it reaches its closest point to the Sun in late October 2025, it may develop a more dramatic tail, giving scientists another chance to study its unusual dust behavior. After that, it will pass Venus in early November, before heading back out toward interstellar space, never to return. The significance of Atlas is not only in its strangeness, but also in what it represents for science. Each interstellar object discovered adds to our understanding of how common such visitors might be, and what they can teach us about other star systems. Before 2017, no interstellar object had ever been identified. In less than a decade, 3 have been observed. The Vera C. Rubin Observatory, with its powerful wide-field surveys, is expected to find many more in the coming years. Some estimates suggest as many as 50 new interstellar objects could be detected within a decade. For now, though, Atlas remains a singular opportunity. Its anomalies, its sunward dust plume, its faint chemistry, its improbable trajectory, its brightness pattern, and its unexplained acceleration are forcing astronomers to rethink their assumptions about comets and interstellar debris. Each new observation provides more data, but also raises new questions. The lack of clear answers is not a failure. Rather, it shows the limits of current models and the potential for discovery. In a broader sense, the study of Atlas reminds us of how science progresses. Anomalies appear, explanations are tested, and sometimes the truth remains elusive for years. Whether Atlas is eventually explained as a natural oddity, or whether it points to phenomena we do not yet understand, it highlights the importance of curiosity and open-mindedness. What Atlas ultimately tells us is that our universe is far more diverse and surprising than we often assume. Objects from other star systems may carry with them entirely different chemistries and structures, shaped by conditions we have never witnessed. By observing them, we get glimpses into worlds we cannot otherwise reach. For now, Atlas is a messenger from the distant past of the galaxy, offering both data and mystery. As it races away after perihelion, astronomers will continue to follow it for as long as possible. Each telescope image, each spectral reading, adds to the record of one of the strangest objects ever seen in our skies. When it finally fades back into interstellar darkness, the legacy of its passage will remain, a reminder that even in a universe governed by natural laws, surprises are still waiting.